Hello and welcome to our third differential equations lecture. Today we're going to be talking about first order differential equations, and we'll talk about three topics of first order differential equations. First, we'll talk about autonomous equations and population dynamics. We will talk about exact equations, and then we will finish by talking about substitutions. Our first topic is autonomous equations and population dynamics. What is an autonomous equation? An autonomous equation is simply an equation of the form dy dt is equal to some function of y. As long as the function is only a function of y, then this equation is an autonomous equation. The first example, let's talk about the number of cats in Istanbul. Let y of t denote the number of cats in Istanbul at time t. We'll start with the simplest model that we can think of. We're going to assume that the rate of change of y is proportional to y. In other words, if there are lots of cats, that means lots of baby cats, and y would increase quickly. If there are a small number of cats in Istanbul, then that means a small number of baby cats, so y will increase slowly. So in other words, we're going to assume that dy dt is proportional to y, or is equal to some constant r multiplied by y. And we're going to assume that the constant r is a positive number. This is a simple differential equation. From 2 weeks ago, we know how to solve this differential equation. We know that the solution to our initial value problem is the initial condition y0 e to the power rt. That means that the solution will increase exponentially, as in this graph. Now, for small values of y, this is a good model. This part of the model is good. We're happy with this. The problem happens when y is a large number, because the model predicts that the number of cats in Istanbul will increase exponentially for all time. And this cannot be true. We have 1 million cats in Istanbul, 1 billion cats in Istanbul, 1 trillion cats in Istanbul. At some point, this is not going to be true. The food will run out, or there'll be no space to fit cats in, or people will be angry with cats, or ... Lots of things that could stop the number of cats increasing once we get to a huge number of cats. So we're going to need a better model than this. For the next model, I want to replace the constant r by a function. Instead of ry in the previous model, now we're going to have some function h of y multiplied by y. And I want the function h to satisfy these three properties. The previous model was a good model if y was small. So if y is small, we want the model to be roughly the same as the previous one. So if y is small, h of y should be approximately equal to r. The problem in the previous model was when y was very large. So in this model, when y gets larger, I want h of y to decrease. And in fact, if y is very, very large, I want h of y to be negative. The simplest function h which satisfies these properties is r minus ay for some number a. We have a function like this. This is h of y, and if this is y, we have a straight line. This is r, and this is some number. In fact, r divided by a. When y is small, the function is approximately equal to r. That's good. The function decreases, and for very large y, the function is negative. So our differential equation looks like this. dy dt is our function, r minus ay, multiplied by y. But I want to write this in a slightly different way. I want to write this as dy dt is equal to r multiplied by 1 minus y over k y for some constant k, which is going to be equal to r over a. This equation in the orange box is called the logistic equation. The first thing we're going to do is we're going to look for equilibrium solutions. In other words, we're going to look for solutions where dy dt is equal to 0. So I'm going to start with dy dt is equal to 0. Or in other words, we're going to start with 0 is equal to r multiplied by 1 minus y over k y. Remember that r is a positive number. This can't be 0. Either y is 0 or 1 minus y over k is 0. In other words, y is 0 or y over k. These equilibrium solutions are important. I'm going to show you some more solutions now, and you'll see that the other solutions either converge to equilibrium solution or they diverge from it. These are some solutions to the logistic equation. We have our two equilibrium solutions, the two horizontal lines. Y is equal to 0 and y is equal to k. And if we look at the behavior of all of the other solutions, solutions are diverging away from y is equal to 0, and they are converging to y is equal to k. I'm going to discuss soon how we can draw these solutions, how we can understand what these solutions look like. To understand the behavior of solutions without first solving the differential equation, you can use this technique. You can draw the graph of dy dt against y. Remember, dy dt was r 1 minus y over k multiplied by y. If we draw the graph of this function, draw the graph of r 1 minus y over ky, we get this curve. Graph is 0 when y is 0, of course. The graph is 0 when y is k. The graph is positive between 0 and k. The graph is negative after k. What can we see from this graph? First of all, we can see that, say, where the derivative is positive, that tells us that y is increasing. And when dy dt is negative, or in other words, y is decreasing. We show this with graphs. When y is increasing, we draw a green arrow to the right because it's getting bigger, so y is moving to the right. And when y is decreasing, when dy dt is negative, y is getting smaller, y moves to the left on this axis. We draw a green arrow to the left. To investigate further, we can look at the second derivative of y. So there is a mistake here. This should say second derivative of y with respect to t. So, second derivative of y with respect to t. In other words, the derivative of dy dt, but dy dt is equal to f of f. So we have the derivative of f. Again, there's a typo here. This bracket shouldn't be a square bracket. This should be a round. When we use the rule, we find that this is the same as f prime of y multiplied by f. So we can say the solution is concave up, positive second derivative, if y double prime is strictly positive. In other words, the graph is concave up when both f and f prime are positive or when they're both negative. You can also say the graph is concave down. Concave down we get when the second derivative is negative. And this occurs when one of f and f prime is positive and one of them is negative. Now, let's go back to the previous graph, the graph with green arrows. We can see that on the first part, between 0 and k over 2, f is positive because the graph is above the y-axis, and this graph is going upwards, f prime is positive. So just here, y must be increasing and concave up. Increasing and concave up means the graph looks like this. On the second part of the graph, between k over 2 and k, again, f is positive, but now f is going down. So f prime must be negative. Because one of these is positive and one of these is negative, you must have concave down. So on this part, y must be increasing and concave down. Increasing and concave down means the solution curves something like this. And then finally, between k and infinity, the graph of f is negative, it's underneath the y-axis, and it's not just negative, it's also decreasing. F is negative and f prime is negative. We saw that if both of these are negative, then we have concave down. So, I mean, they're both negative, we should have concave up. Another mistake here. Increase and concave up means the solution curves like this. There's one more bit of information we can use. You recall the final theorem from last week's lesson said that two solutions to first order equations cannot intersect. They can become close together, but they can never cross each other. So putting all this information together, we can draw some solutions. I haven't solved the equation, but I've got enough information to draw these solutions. We have the two equilibrium solutions first. Between 0 and k over 2, the solutions are increasing and concave up. Then between k over 2 and k, the solutions are increasing and concave down. And then finally, in the top part of the graph, the solutions are decreasing and concave up. This is enough information for us to sketch some solutions to the graph. Without solving the equation, we've still gained a lot of information about the solutions to this equation. We can classify the equilibrium solutions. Note that because the solutions are curving towards y is equal to k, the graph looked like this. This was k. The solutions were curving, converging towards it, like this. We say that y is equal to k is an asymptotically stable equilibrium solution, or equivalently, we can say it's an asymptotically stable critical point. Solutions were moving away from y is equal to 0. We say that y is equal to 0 is an unstable equilibrium solution, or an unstable critical point. We just recap. Remembering I was drawing green arrows on the graphs before. Green arrows can tell us how to classify an equilibrium solution. The green arrows move towards an equilibrium solution. In other words, if all of the arrows are moving towards it, if we have two arrows and they both move towards it, or depending on the domain of our equation, maybe we only have one arrow and that arrow is moving towards it, then the equilibrium solution is asymptotically stable. If all of the arrows are moving away from the equilibrium solution, then the equilibrium solution is unstable. And if we have two arrows, one of which is moving towards it and one is moving away, we say that the equilibrium solution is semi-stable. For example, you have this type of question in your homework. Find all of the critical points or all of the equilibrium solutions of this equation and classify each as asymptotically stable, unstable, or semi-stable. Our equation is dy dt is equal to y multiplied by 1 minus y squared. This function is our function f of y. And I'm interested in looking at this for any y between minus infinity and infinity. May answer examples I restrict y, but for this one, or if I don't say, we should assume that y is between minus infinity and infinity. So what do we do? The first thing we do is we draw the graph of f of y against y. You can use a computer or a calculator, or you can just draw this roughly by hand. If we're drawing this by hand, where is this equal to 0? We can ask. For this equal to 0, we must have that y is 0, y is minus 1, or y is equal to 1. So we must be passing through these 3 points. We can then look at the value of our function between these. So for example, let's suppose we look at a half. Put a half into the equation, a half, and then 1 minus a half squared, or 1 minus a quarter. Is this positive or negative? This is a positive number, so the graph must be positive between these 2 points. We can, for example, look at 2. Put in 2 and then 1 minus 4. This is a negative number, so this part of the graph must be negative. We don't need the exact shape of the graph, we just need to know where is the graph positive, where's the graph negative. And then after we've drawn the graph, we can draw the green arrows. On the left part of the graph is positive. Now we have positive graph, we draw an arrow to the right. And the graph is negative, so we draw an arrow to the left, and an arrow to the right, the graph is positive, and then finally we draw an arrow to the left. The critical points, we've talked about this already. Critical points are minus 1, 0, and 1. And we can classify these. First of all, at minus 1, the arrows are moving towards it. This must be asymptotically stable. At 0, both of the arrows are pointing away. This is unstable. and that 1 must be stable. Y is equal to -1 is an asymptotically stable equilibrium solution. Y is equal to 0 is unstable, and Y is equal to 1 is asymptotically. And find all the critical points or find all the equilibrium solutions of this differential equation, where again I'm letting y be any number between -infinity and infinity, and classify each as asymptotically stable, unstable, or semi-stable. We draw the graph of f of y against y, and we draw the green arrows. The graph is negative, arrow to the left. The graph positive, so arrow to the right. And the graph is positive, so arrow to the right. We can see that we have two critical points, or two equilibrium solutions, 0 and 2. At 0, both arrows point away, so unstable. At 2, one of the arrows points towards 2, one of the arrows points away, so semi-stable. Y is equal to 0 is unstable, y is equal to 2 is semi-stable. Now let's go back to modeling the number of cats in Istanbul. This time I want to look at a slightly different equation. I want to look at dy dt is minus r, 1 minus y over t, y. This is different from the logistic equation because now we have minus here. Again, r and t are our positive constants. To understand this, we draw the graph of f of y, or in other words, minus r, 1 minus y over t, y, against y. And the graph looks like this. We have two critical points, or two equilibrium solutions at 0 and at t. I'm only drawing the positive y-axis because I can't have a negative number of cats in Istanbul. So we start at 0 and we go to infinity. At 0, there's only one green arrow here and it's pointing towards it, so this must be asymptotically stable. At t, both of the arrows are pointing away, so this must be unstable. With this information, we can sketch some solutions. And what we do is we choose somewhere to start. Let's say I start just here. Green arrow points downwards. That means the solution must go downwards. Goes down like this. Green arrows point downwards. We still keep going downwards. Remember, we can't cross 0, so now we have to curve upwards. We get close to 0, but we can't cross 0. Or I might want to start at this point. The green arrow points upwards, so the solution must be increasing. The solution must curve up something like this. Just with the information about equilibrium solutions, unstable, semi-stable, or asymptotically stable, we can sketch the solutions like this. Now, depending on the initial condition y0, we have either the solution tends to 0 or the solution tends to infinity. This number t is called a threshold level. Below this level, there's no growth. Solution goes down to 0. The population of some species in the world does have this threshold. This means if there's not enough of the species in the world, then the number of animals in the species decreases to 0 and the species becomes extinct. This model predicts that the number of cats in Istanbul will increase to infinity, and we don't want this. This was a problem with the first model, so we need a more advanced model. I want to combine logistic equation with the equation with a threshold. Now I want to look at this equation. Minus r, 1 minus y over t, 1 minus y over k, y. This k term, or in fact, all of this bracket, this gives us this logistic property. This bracket, 1 minus y over t, gives us a threshold. And you might ask, why is it minus at the top? It's minus so that y is positive, dy dt. So that this is always, let me say that again. Why do we have a minus sign here? It's minus sign so that the number of cats will increase under the correct conditions. One final thing I didn't say, here we're assuming that t is between 0 and k. If we draw the graph of y prime against y, or in other words, the graph of f of y against y, the graph looks like this. Draw the green arrows. Y is equal to 0 is asymptotically stable. Y is equal to t is unstable. Y is equal to k is asymptotically stable. So solutions look like solutions converge to the asymptotically stable k and 0. Solutions diverge from t. And this is actually quite a good model. This is a model which has been used by biologists to study the populations of certain animals. Our next topic is the topic of exact equations. Last week we looked at two special types of first-order equations. We looked at linear equations and we looked at separable equations. Now we're going to look at another special type of first-order differential equation. For example, I want to solve 2x plus y squared plus 2xy, y prime is equal to 0. If you look at this equation, you will see this equation is not linear. It's not linear because we have y multiplied by y prime. And this equation is not separable, which I will leave you to think about. So we can't use the techniques from last week. We need a new method to solve equations like this. And the method relies on us finding a special function called psi. This is the Greek letter psi, or psi. Note that if we've found the special function psi, which is x squared plus y squared, and then we take partial derivatives of this function, the partial derivative with respect to x is 2x plus y squared, or first part, and the partial derivative with respect to y is 2xy, or the second function. So in other words, if we know this special function psi, then our differential equation is just psi dx plus psi dy dx is equal to 0. And if you recall your chain rule for partial derivatives from Mathematics 2, you will remember that what we have here is just d dx of psi. So in other words, the differential equation is really just d dx of x squared plus xy squared is equal to 0. Our function has 0 derivative, so in other words, our function must be equal to a constant. And this is the solution to this differential equation. The solution is x squared plus xy squared is equal to a constant. The key step to solve an exact equation, an equation of this form, is to find this function xi. If we know xi, then we can just write down that the solution to the differential equation is xi is equal to a constant. So how do we find the function xi? Consider this differential equation. Consider m a function of x and y, n a function of x and y prime is equal to 0. If m and n, if it's possible to find the special function xi such that xi dx is equal to m and xi dy is equal to n, then equation 2 is called an exact equation. And if the equation is exact, we can use the method from the previous example, and we can find that the solution to the differential equation is just xi is equal to c. So, to solve an exact equation, 1, we must find the special function xi, and then step 2, write the solution is xi is equal to a constant. Before I go on, I want to introduce some notation. For an ordinary derivative, dy dx, we can write this as y prime. Partial derivatives, df dx or df dy, I want to use this notation, f subscript x and f subscript y. And we have a theorem. First of all, let's just be careful. Let's suppose mn, partial derivative of m with respect to y and partial of n with respect to x, are continuous on some rectangular region. This is just me being careful. Then differential equation m plus ny prime equal to 0 is the exact equation if and only if, and this is the important equation to remember, and only if my is equal to nx. Let's do an example. Consider this differential equation. Y cos x plus 2x e to the power y plus sine x plus x squared e to the power y minus 1 multiplied by y prime is equal to 0. Good question. Is this equation exact? And if the answer is yes, then solve this equation. You have 2 questions like this on your homework. So what do? First of all, we find m. Is m. M is y cos x plus 2x e to the power y. And we need to find n. Is my n. N is sine x plus x squared e to the power y minus 1. I need the y derivative of m and the x derivative of n. If these are the same, then the equation is exact. Differentiate m with respect to y. When we do partial derivatives, we pretend that x is just a number. So let's pretend that sine x is just a number. The derivative of a number multiplied by y is just a number. Just get cos x. Pretend that 2x is just some number. 2x, and then the derivative of the power y is e to the power y. And differentiate n with respect to x. Derivative of sine x is cos x. Derivative of x squared is 2x. E to the power y, we'll just pretend this is a number, keep this the same. And the derivative of minus 1, of course, is just minus 0. Now look at these two functions. These two functions are the same. Because my is the same as nx, this means that the equation is exact. This means it's possible to find the special function xi. This means that there exists a function xi such as xi x is equal to m and xi y is equal to n. We must find this function xi. Here are our two equations. We need to choose one of these equations. It doesn't matter which one we choose, but just for this example, let's suppose we choose the first one. I'm going to take the first equation and I'm going to integrate it with respect to x. WRT is a common abbreviation for with respect to. In other words, it means when we do the integral, we're going to integrate with dx on. So we're going to integrate this function with respect to x. Y stays the same. So we get y, and derivative of cos, sorry, the integral of cos x is sine x. For the second term, integral of 2x e to the power y. E to the power y stays the same. We're pretending this is a constant, then this is a number. Integral of 2x is x squared. Now, you will record from MATH2, when we do an integral involving two variables, we don't do plus a constant on the end. Instead, we have to add on a function. And if we're integrating dx, you must add on a function of y. If I did integral of, let's say, half y, but dy, x stays the same. Integral of, sorry, let's make that 2xy. Integral of 2y is, of course, y squared. And then we need to add something. Because we're integrating with respect to y, we must adding on a function of x. And just think about this. This needs to be the opposite of differentiation. If I take, for example, this function, and I take the x derivative of this function, I take the derivative of y sine x, y cos x, plus the derivative of x squared e to the power y, that's 2x e to the y, plus the derivative of h of y with respect to x, but that's plus 0. So we would go back to where we started. So what we did was, recap, I started with the first equation and I integrated with respect to x. And then I want to differentiate with respect to y. I want to take y sine x plus x squared e to the power y plus h of y, and I want to differentiate with respect to y. To get sine x plus x squared e to the power y plus h prime of y. Wait a minute, we already have an equation for h of y. Our second equation says y is sine x plus x squared e to the power y minus 1. So now I have two equations for xi y. And these must be the same. Sin x plus x squared e to the power y plus h prime of y must be the same as sin x plus x squared e to the power y minus 1. In other words, we must have that h prime of y is minus 1. We can choose any function h as long as this equation is satisfied. We don't need to find every possible value of h, we just need to find one. So we could choose h of y is equal to minus y. And that's what we need. We know that xi is y sine x plus x squared e to the power y plus h of y, and now we know h of y. So now we know xi. Xi must be y sine x plus x e to the power y minus y. And as soon as we know xi, we know the solution to the differential equation is just this function is e c. Now let me recap what I did. We started with two equations. We choose one of these equations, it doesn't matter which one, but I decided to choose the first equation. I integrated this equation and then I differentiated it. Because I'm starting with the first equation, xi x, I integrate with respect to x, and then I differentiate with respect to the other variable y. I look at the second equation and I must find h. As soon as I found h, I know xi, and as soon as I know xi, I know the solution to the differential equation. Let's do another one. Consider y e to the power xy, that's e to the power xy, y prime is equal to 0. Is this equation exact? And if the answer is yes, solve this equation. We write down m and n. M is y e to the power xy, and n is e to the power xy. And we differentiate these functions. My is e to the xy plus x, y e to the xy, and nxy e to the xy. These functions are different. So, is the equation exact? The answer is no. Because these equations are different, it means that the equation is not exact. For this example, we're finished. The example is not exact, so we're finished. Another one. Consider 4x cubed, y cubed plus 1 over x plus 3x to the power 4y squared plus 1 over y prime is equal to 0. Is this equation exact? And if the answer is yes, solve this equation. I'm going to leave one for you to do. I want you to check that if this is m and if this function is n, check that my is equal to n. You'll find that this is true. You'll find that this equation is exact. And then start with the equations xi x equal to m and xi y is equal to n. Choose one of these equations, it doesn't matter which one you choose, and integrate it. If you choose the first one, you must integrate with respect to x. If you choose the second equation, you must integrate with respect to y. After you've integrated, differentiate with respect to the other variable. You integrate with respect to x first, then you differentiate with respect to y, or if you choose the second equation, first integrate with respect to y and differentiate with respect to x. After you found the function h, you know xi, and after you know xi, you know the solution. I leave this for you to do as practice. Check that the solution to this equation you get is x to the power 4 y cubed plus the natural logarithm of the absolute value of x plus the natural logarithm of the absolute value of y is equal to some constant c. Next example. Consider 3xy plus y squared plus x squared plus xyy prime is equal to 0. Is this equation exact? And if the answer is yes, solve it. Note that my is not equal to n. This equation is not exact. So the method I've shown you will not work for this equation. But I want to try it anyway. I want to show why this method will not work for an equation which is not exact. So let's suppose we're trying this method anyway. Let's suppose that it does exist, this function psi. We know from the theorem that the equation is not exact. We know that in fact it does not exist. So let's just suppose we try to find it. Choose the first equation and integrate with respect to x. And then differentiate with respect to y to get 3 over 2 x squared plus 2xy plus 8 y. But we already know that xy is x squared plus xy. Rearranging this, we need to find h of y. So h prime of y is minus a half x squared minus xy. Now you'll see there is a problem here. On the right hand side I have x and I have y. On the left side I only have y. In other words, it's not going to be possible to find h. H must be a function of y, but the right hand side depends on both x and y. Not possible to find h, so it's not possible to find xi. Xi does not exist. So our method failed. Why did our method fail? Our method failed because my is not equal to nx. Our method failed because the differential equation is not x. But it is still possible to solve an equation like this. Sometimes, not always, but sometimes it's possible to convert a differential equation which is not exact into an exact equation by multiplying it by an integrating factor. Remember how we solved linear equations last week? We found an integrating factor and we multiplied the equation by the integrating factor. We have a similar idea here. We're going to find a special integrating factor and then we're going to multiply our equation by the integrating factor. Let's start with this equation and let's suppose that this equation is not exact. And let's suppose that we multiply this by some unknown function, mu. By a theorem, by an equation in the theorem, we know that the equation is exact, this new equation is exact, if and only if the y derivative of xi m is the same as x derivative of mu m is the same as the x derivative of mu n. So we're interested in y derivative of mu m and x derivative of mu n. Rearranging this, we have a partial differential equation, m mu y minus n mu x plus my minus nx, mu is equal to 0. If we can find an integrating factor which solves equation 5, then equation 4 is exact, and we know how to solve exact equations. But equation 5 is a first order partial differential equation, and partial differential equations are typically not easy to solve. We are in danger of making our problem more difficult instead of more easy. How can we make this easier? Instead of looking for a general integrating factor mu of xy, instead we could look for an integrating factor mu which only depends on x. And this makes it easier because it means mu of y is now equal to 0. And equation 5, instead of the complicated equation on the previous page, just simplifies to mu dx is equal to my minus x divided by n mu. Now, if this function, so if this function in brackets my minus x over n is a function only of x, then equation 6 is an ordinary differential equation, and we can solve this. In other words, my minus nx over n is a function only of x, then we can find an integrating factor of x. Note that this equation is both linear and separable, so we know how to solve this differential equation. We could do the same idea, but instead looking for an integrating factor which only depends on y. Then we would have a very similar equation. Instead of my minus nx over n, we have nx minus my over m mu is equal to mu dy. If we were having exams in a classroom, you would be expected to remember these two equations. If we're having online exams, which I'm assuming we will do, please make sure that you have equation 6 and equation 7 written down on a piece of paper next to you in case I give you a question needs them. So, solve 3xy plus y squared plus x squared plus xy y prime is equal to 0. We looked at this equation before, and we know that this equation is not exact. We're going to try to find an integrating factor. We have m and n, my and nx, and we calculate my minus nx divided by n and nx minus my over m. My minus nx over n. When we simplify this, we get a nice simple function, 1 divided by x. When we look at nx minus my over m, we have this complicated thing, minus x minus y over y, 3x plus y. The first one is a function only of x. The second one is not a function only of y. So we're going to use the first one. We're going to use 1 over x. Because my minus nx over n is a function only of x, it will be possible to find an integrating factor mu of nx. Because nx minus my over m is not a function only of y, not possible to find an integrating factor mu of y. Now, you know how to solve this equation. Our differential equation, which you will be remembering or writing down for an exam, d mu dx is equal to my minus nx over n mu. For us, is just differentiation. D mu dx is equal to mu divided by x. This is a separable differential equation, and you know how to solve this. We can separate the variables. The mu we can take to the left, the dx we can take to the right. And we get d mu over mu is equal to dx over x. All of the mu terms on the left, all of the x terms on the right. We've separated the variables, therefore we're allowed to integrate this. And after we've integrated, rearranged, and simplified, we find that mu must be cx for some non-zero constant c. We don't need to find every possible mu that works. We only need to find one integrating factor which works. So we can choose any value of c, and because I like easy numbers, I'm going to choose c is equal to 1. So we have the integrating factor mu is equal to x. What we do is we take our original differential equation and we multiply by x. And there must be a mistake here. There's some mistake just here. What should it have been? Let's see. Okay, we're going to take this equation and we're going to multiply it by x. So we're going to get 3x squared y, and then plus x y squared. First bracket. Second bracket multiplied by x, we're going to get x cubed, and then plus x squared y prime is equal to 0. So where are we? 3x squared y plus x squared y squared. So this should be plus x instead of a little x. You will note that this differential equation is exact. If we take the y derivative of the first term and the x derivative of the second term, we get the same function. And we know how to solve exact equations. We need to find some special function xi such that xix is equal to m and xiy is equal to n. We take these two equations, we choose one of them, it doesn't matter which one we choose. I'm going to choose the first one, and I'm going to integrate the first one with respect to x. And integration of 3x squared y, x cubed y. Integral of x y squared is a half x squared y squared. And then instead of plus a constant, let's do plus a function. Because we're integrating with respect to x, the function must be a function of y. And then differentiate this. The derivative of this with respect to y is x cubed plus x squared y plus h prime of y. And compare this to the second equation. We know that this must be the same as x cubed plus y. We have x cubed and x cubed. Yes, x squared y and x squared y. What are we left with? We're left with h prime of y and 0. We can choose any function h such that h prime of y is equal to 0. Choose the easiest one. I choose h y is equal to 0. So we know xi must be x cubed y plus a half x squared y squared. As soon as we know xi, we know the solution to the differential equation must just be xi is equal to a constant. Another example. Solve y e to the power xy plus 2 over y plus x multiplied by e by xy, y prime is equal to 0. This differential equation is not exact, which I leave for you to check. We calculate my minus nx over n, and we see this is a complicated thing with both x and y, and we don't want this. And we calculate nx minus my over m, and this is just a function of y. This is what we want. So we're going to look for mu of y. We need to solve d mu dy. There's a mistake here. There should be a y here. No, sorry, I'm wrong. There should be a mu here. There should be a mu here. There should be a mu here. And I'm going to leave this for you to finish. When you solve d mu dy is equal to 2 mu divided by y, you'll find that you get the integrating factor mu is equal to y squared. So we multiply our differential equation by y squared, and we get y cubed e to the power y plus 2y plus xy squared e to the power xy prime is equal to 0. This equation should now be exact, and I'm going to leave the rest of the solution to you. Use the method we've used before, and you will find the solution must be y squared e to the power xy is equal to c. Final topic for today. Today is going to be a long lesson. The final topic for today is the topic of substitutions. Remember how we do integrals like this. The integral of x squared sine x cubed dx. What we do is we use a substitution. In this case, we use the substitution u is equal to cubed, and we change this difficult looking integral into easy integral. Sometimes we can use the same idea to solve differential equations. We can use a substitution to turn a difficult equation. Suppose I want to solve this differential equation. And let's suppose I can use a substitution to change this into an easy differential equation. Then we solve the easy differential equation and then substitute again to get to y. In this course, we're going to use substitutions to solve two special types of first order differential equation. We're going to solve homogeneous equations and we're going to solve Bernoulli equations. If you buy the first textbook which I suggested, Boyce's Elementary Differential Equations, it doesn't have a section on substitutions. In fact, instead, this is just hidden in the exercises somewhere. By the second book, it has a nice section on substitution. First of all, homogeneous equations. What is a homogeneous equation? A homogeneous equation is an equation which we could write as dy dx is some function of y divided by x. So, for example, dy dx is cos of y of x, or dy dx is cos of x divided by y. Or dy dx is y of x cubed plus y of x. Or dy dx is y of x minus 4 divided by 1 minus y of x. Anytime we have a differential equation where the right-hand side is always a function of y divided by x, or could be rearranged like that, then we have a homogeneous equation. And for homogeneous equation, we use the obvious substitution. We're going to replace every y divided by x by v. Now, note that v equal to y of x is the same as writing y is equal to xv. And if we differentiate this using the product rule, we get v plus x dv dx. We're going to be using these equations. We're using v is equal to y over x, and we're going to use y dx is equal to v plus x dv dx. For example, solve dy dx is equal to y minus 4x divided by x minus y. This is a homogeneous equation, which you will see if we divide by x. To write this as y over x minus 4 divided by 1 minus y over x. We're going to use the substitution v is equal to y over x. Instead of writing y over x, we're going to write v. So this becomes v minus 4 divided by 1 minus. I also need to use a substitution on the left side. Instead of dy dx, we're going to use the substitution v plus x dv dx. So our differential equation becomes v x dv dx, v minus 4 divided by 1 v. And I want to move the v to the right side. This v I want to move to the right side by subtracting v on both sides. Put everything over 1 minus v and simplify. I get v squared minus 4 divided by 1 minus v is equal to x dv dx. Now note that this is a separable equation. You know how to solve separable equations. So the question which I'm going to go through quite quickly should just be revision for you. If you rewatch this lesson, you can slow this down and check it more carefully. I can rearrange this so that all of the v terms are on the left, and all of the x terms are right. I can use partial fractions on the left side, and then I can integrate and rearrange, find that the solution is absolute value of vx plus 2x cubed multiplied by the absolute value of vx minus 2x is equal to constant. Please check through this. You will see that you know how to do this. Now that we have an equation for v, the final step is to find an equation for y. We're going to substitute back in. We know this is the equation for v, and we also know that y is equal to vx. So instead of vx, we can write y, and just here, instead of vx, we write y. And we find the solution. The solution to this homogeneous equation is the absolute value of y plus 2x cubed, absolute value of y minus 2x is equal to a constant c. Let's run through the method. First, we do the substitution. We substitute that v is the y of x, and using the product rule, we also know that dy is v plus x dv dx. Always for a homogeneous equation, we do these substitutions. Then we solve a separable equation. you know how to solve separable equations. And then step 3, do the substitution again. Everywhere we find a Vx, we replace this with 1. One more example. Solve dy dx is equal to x squared plus 3y squared divided by 2xy. First, we rearrange this by dividing by x squared. 1 plus 3y squared over x squared divided by 2y over x. You can see this is a homogeneous equation because everywhere y appears, we also have divided by x. So we do our substitutions. Instead of y over x, we write v. We're going to get v squared and v instead of y over x squared and y over x. And we do the substitution. Instead of dy dx, we have v plus x dv dx. Move the v to the right-hand side and simplify. We get x dv dx is equal to 1 plus v squared divided by 2v. This is a separable equation. You know how to solve separable equations, so I'm going to leave this for you to do. You can check that the solution to the separable equation is 1 plus v squared minus 2x is equal to 0. And then finally, we do our substitution again. Instead of v, we can write y over x and then rearrange to find the solution to this differential equation is x squared plus y squared minus cx cubed is equal to 0. All we're doing is substitution, solve a separable equation, and then substitution again. On your homework, you have one homogeneous equation to solve. And the final idea for today's lesson is Bernoulli equation. Bernoulli equation is the equation of the form y prime plus pty is equal to qt y to the power n. And this is y to the power n, which is also the part here. For a Bernoulli equation, we always use this substitution. This is the formula to remember for a classroom exam, or this is the formula to make sure you have written down on a piece of paper close to you if we're doing an online exam or for the homework. But Bernoulli equation, we always use the substitution. P of x is equal to y to the power 1 minus n. I'm going to solve 2 examples. Solve dy dx minus 3 over 2x y, 2x y to the power minus 1. I have a function of x just here. I have a function of x, and then I have y to the power n. In this case, n is equal to minus 1. So note first that this differential equation has n equal to minus 1 just here. We always use the substitution v is equal to y to the power 1 minus n, which for us is 1 minus minus 1, or y squared. To solve this differential equation, we're going to use the substitution v is equal to y squared. Now, if v is equal to y squared, that's the same as saying that y is equal to the square root of v. And using the chain rule, that means dy dx is dy dv dv dx, or half v to the power minus a half dv. Let's substitute this into our differential equation. Our differential equation is dy dx, which I've written in green. We know what this is going to be. Minus 3 over 2x y. We're going to use this orange substitution is equal to 2x y to the power minus 1. Again, I'm going to use the orange substitution. Instead of dy dx, I'm writing a half v to the power minus half dv dx minus 3 over 2x. Instead of y, I'm doing a substitution. V to the power half is equal to 2x, and then instead of y to the power minus 1, we write v to the power minus a half. We can simplify this by multiplying by 2v to the half. And look what we have. We have dv dx minus 3 over xv is equal to 4x. This is a linear equation, and you know how to solve linear equations. Just by doing this substitution, we've changed this complicated Bernoulli equation into an easy linear equation. The following calculation should be revision for you. I'm going to be quite quick. We use an integrating factor. In this case, we use the integrating factor x to the power minus 3. Multiply this by the integrating factor. Use a product from the left side, and we find ddx of x to the power minus 3b is equal to 4x to the power minus 2. Integrate this, and we find our formula for v. And then finally, all we need to do is do our substitution. Everywhere we see v, we write y squared. We find that the solution is y squared is equal to minus 4x squared, some constant x cubed. Let's recap. To solve a Bernoulli equation, the substitution that we always use is v is equal to y to the power 1 minus n. After we've done this substitution, we solve a linear equation, and then we do our substitution again, and we end up with our equation for y. I'm going to do one final example. We'll do the substitution, we'll solve a linear equation, and then we'll substitute again. Solve x dy dx plus 6y is equal to 3x and y to the power 4 divided by 3. This time, we have that n is 4 divided by 3. So the substitution v we're going to use is y to the power 1 minus n, which for us is y to the power minus 1/3. Rearrange this to see that y must be equal to v to the power minus 3, and dy dx must be minus 3v to the power minus 4 dv dx. If we substitute these into our differential equation, we have this complicated thing. Minus 3x v to the power minus 4 dv dx plus 6 v to the power minus 3 is equal to 3x v to the power minus 4. But we can simplify this to a linear equation. dv dx minus 2 over xv is equal to minus 1. Linear equations we know how to solve. Using the integrating factor x to the power minus 2, please check that the solution to this linear equation is e is equal to x plus some constant x squared. And then finally we substitute again. V is equal to y to the power minus 1/3, and we find the solution. Rearrange, and please check this is correct. Y is equal to 1 divided by x plus c x squared, and then all cubed. And this is the end of today's lesson. Next week, we do not have a lesson because next Thursday is Republic Day. So that means our next lesson is 2 weeks from now. In 2 weeks, we're going to start talking about second and higher order differential equations. We'll cover sections 3.1, 3.2, and 3.3. If you have any questions for me, you can now type them in the chat. This is the end of the lesson, so you may leave if you wish. I'm not going to solve the homework questions because the homework questions are open until January. But I can show you a similar problem from a previous lecture. Have a look. So the last question in the first homework is about separable equations. Let me load up a nice example. Here we go. This is a separable differential equation. dy dx is x squared divided by 1 minus y squared. What we want to do is we want to separate the variables. I want to move all of the y terms to one side of the equal sign, and I want to move all of the x terms to the other side. So this 1 minus y squared, for example, I can multiply by both sides by 1 minus y squared to move this to the left. And then dx, if we multiply both sides by dx, we can move this to the right. So in other words, this differential equation I could write as 1 minus y squared dy is equal to x squared dx. Multiply both sides by 1 minus y squared, multiply both sides by dx. Because all of the y terms are on the left of the equal sign, all of the x terms on the right side, we are allowed to integrate this equation. So we can put an integral sign on both sides. Integral of 1 minus y squared, when we integrate this, it's of course 1 minus 1/3 y cubed, equal to the integral of x squared, that's 1/3 x cubed, and then we need to add a constant plus c. And I hope you can read this. This is how we get the solution to this differential equation. Let's see if I can find another. Here's another problem. This is an initial value problem. Solve dy dx is equal to 3x squared plus 4x plus 2 divided by 2, 1 minus 1. This is similar but more difficult to question 7 on homework 1. We use the same method. First, I want to separate the variables. 2y minus 1 move to the left by multiplying both sides by 2y minus 1. And dx, I want to move to the right by multiplying both sides by dx. And then I get 2y minus 1 dy is equal to 3x squared plus 2 dx. Because we've separated the variables, we're allowed to integrate both sides. In other words, we're allowed to put an integral sign on the left side and on the right side. And we can calculate these integrals to get. This is a general solution to the differential equation. To solve the initial value problem, we need to choose the value of the constant c to satisfy y of 0 and minus 1. And for this problem, we need to choose c is equal to 3. So we get the solution like this. Y squared minus 2y is equal to x cubed plus 2x squared, 2x plus 3. If you use the same method, you can solve the problem on homework. Are there any more questions? Okay, so if there are no more questions, we can end the lesson here. If you think of a question later, you can ask me via the discussion board. If you want help with the homework, you can ask me there. Other students may help you, or I can give help via the discussion board.